Okay, so for this normal vector, actually, for this vector, it is perpendicular to the plane passing through PQR. But actually, for this one, if I ask you this question, if we divide by 5, and divide by -5, so you will get, divide by -5, you will get 8, 3, -3. This vector. Is this vector also perpendicular to the plane passing through PQR? Is this vector also perpendicular to the plane passing through PQR? Actually, for this one, if you check it, if you denote it by V, if you check it, it will also perpendicular to PQ, and it will also perpendicular to PR. Yeah, so it's also a normal vector, our normal vector here. So it means that for this vector, actually we could multiply by any scalar, or divide by any non-zero scalar. It's also perpendicular to the plane passing through PQR. The reason is that when we check this one, it means that we should consider the inner product, right? The inner product. And here, if we say it's their orthogonal, means that we consider the inner product, right? And what's the relationship? V and N. V is just the some scalar C times normal vector N, the vector N. So, and here we consider inner product. Inner product, then, for example, here N is the ABC, or here I denote it by A1. It will be better to denote it by A1, A2, and X, Y, Z. And PQ is some vector, for example, W1, W2, W3. Then we consider their inner product is XW1 plus XYW2 plus GW3. And now, if we consider vector V is just the some scalar times the vector N. So, for example, we multiply by C, so it's CX, CY, CG, right? So now, when you consider the inner product, it becomes CX times W1 plus CY times W2 plus CGW times W3, right? So what's the relationship? Actually, we just multiply by C for the scalar. We just multiply by C. So of course, if it's equal to 0, it's also equal to 0. It's also equal to 0. So if we just, for the vector which is perpendicular to the plane, then we could, once we multiply by any scalar, non-zero scalar, it's also a vector which is perpendicular to the plane. Yeah. And as we say, in next section we will construct a plane which pass through these 3 points. And the idea is this one. Here I tell you the idea, and we will say more next time here. So the idea is this one. If we have a vector, the normal vector, here I use another notation. So if we have the normal vector, it's a vector perpendicular to the plane. And if we have a plane S, and we have a point, if I give you a normal vector, it means that I give you a vector which is perpendicular to the plane S. And I also give you a point P0. It's in the plane S, so I denote it by X0, Y0, Z0. And it's the normal vector. And P0, X0, Y0, Z0 in S. Yeah, so it's a normal vector N. Yeah, which is cycle. Yeah. Okay, so once I give you a vector which is perpendicular to the plane S, and I give you a point P0 in the plane S, then we could figure out the plane S. We could characterize the plane S and how to solve it. For this normal vector, of course, for the vector, we could move it in parallel. So we could move it in parallel. So we could let its initial point over here. So it's our, we could move it to here. So it's our normal vector n. It's our normal vector n here, and the vector is ABC, right? And now for any point in the plane S, we denote by P, X, Y, Z. It's any point in S. So if I denote by here, so if I denote by X, Y, Z. Okay, and now we consider this vector P0, P0, P, P0, P, P0, P, P0, P. P0 is the start, is the initial point. P is the terminal point. So terminal subtrate initial. S subtract 0, Y subtract Y0, Z subtract Z0. I should mention that X0, Y0, Z0 is fixed. It's given. It's given point, and it's also given normal vector. Then we could calculate the plane S. And X, Y, Z is any point in the plane. It's any point in the plane S. Any point in the plane S. Any point in plane S. So as we say, n is a vector perpendicular to the plane S. So now we have a vector P0P. It's also in S. So of course we know that n is orthogonal to the vector P0P. P0P. Right? P0P. This one. So they are orthogonal means that their inner product equals 0. So it means that their inner product equals 0. Their inner product equals 0. So you could write down n is the vector. P0, P is the vector. So the inner product equals 0. So we could write down here. So first term is A times X subtract 0 plus B times Y subtract Y0 plus C times Z subtract Z0. Z subtract Z0 equals 0. So the point X, Y, Z satisfy this equation. So I write down here. So the plane S satisfy this one. So it satisfies X, A times B times this one plus C times this Z subtract Z0. It satisfies this equation. And if you use the distribution, then you will get AX plus BY plus CG. Subtract AX 0, subtract BY 0, subtract CG 0. So the plane S satisfies this equation. Yeah, and here ABC is given, and X0, Y0, Z0 is given. So for this one, we could exactly calculate the plane S. And for its coefficient, actually for its coefficient, ABC, for the coefficient about X, Y, Z, it's exactly the normal vector. In other words, if I give you a plane, for example, if I give you X plus 2Y plus 3Z, subtract 1 equals 0, then we could figure out a vector which is perpendicular to the plane, right? I mean, we could figure out the normal vector for this plane. Actually, it's exactly the coefficient 1, 2, 3 is enough. This vector is what we want, right? Use the argument. You could know that. Okay, so for the normal vector and for the example to figure out the plane, I will tell you next time. And it's exactly the material in section 5.